Welcome, humanoids. This is episode 5 in our course on philosophy of climate change. This is the introductory lecture to module 2, which is all about climate science. We're going to ask some basic questions today, like what the heck are all these people marching for? What do you mean march for science? With me, as always, is Admiral Akbar at your service doing the technology. This is his favorite subject. He's a big science geek. In fact, he said, what was that? Yeah, he says that the state of our science is primitive. Let's put it that way. I think I got the translation right. I'm a little bit upset with the Admiral because I already taped this whole lecture, got to the end of it, and we had a technical malfunction. So here we are doing it again. And, you know, that's his job. I don't know what's going on. Okay, let's jump into it. Oh, new feature. New feature. I hope that you're seeing this. This is Akbar approved tweets. That's right, this one from Stephen Colbert made him chuckle. And if you have a good climate change tweet, send it my way and you might be featured. If Akbar approves, we'll put it in there. Okay, now to the serious stuff. What are we going to do today? First of all, again, this is to welcome you to Module 2. I just want you to have a sense of what's going to happen in this module. So what's the organization? What's the content we're going to cover? So we're just going to kind of superficially hit it today. And then I also want us just to start thinking about what is science, what is climate science, and why is it so important? So why does science matter? I'm going to run through why it matters for our problem-oriented inquiry, which is we learned what we're doing. Some of the ethics involved with science and science in a democracy. And then we're going to go through different ways of looking at science. What is it? Science is manifold, or at least it's open to many different ways of framing it. When you see those numbers, like science as a body of knowledge, that's going to be episode 6. So our next lecture will be on science as a body of knowledge, and then we're going to talk about institutions, methods, and tools. 9 and 10, we're going to talk about ways of understanding climate science more broadly, and then we're going to wrap up this module asking ourselves, okay, so what are climate scientists saying now in terms of where are we at and what needs to happen? All right, first of all, let's go back to our problem-oriented inquiry. These are tools I want us to use throughout the class. Start with goals. Here's one from the UN Framework Convention on Climate Change, which is one of the institutions we'll cover in that lecture. Goal is to stabilize greenhouse gas concentrations, quote, at a level that would prevent dangerous anthropogenic, human-induced interference with the climate system. Trends with respect to this goal, well, as you can see on the right, greenhouse gas concentrations are going up. That's a problem when you have trends that aren't aligned with the goal, right? What's causing these trends? Well, really roughly, right? Human activities, fossil fuel consumption, as 2/3 of it at least probably in agricultural land use issues, deforestation, all of that. What's going to happen in the future? Projections. Well, we may be approaching dangerous levels. Of course, what is dangerous? That gets to the rhetoric, the hermeneutics, the ethics, the politics of climate change. And then alternatives. Well, there's really 2 or 3 big buckets of climate policy alternatives. Adaptation, which is making us more resilient, our systems more resilient on a planet whose climate is always changing, but now changing perhaps more rapidly and radically than before. And mitigation, which is let's reduce our greenhouse gas emissions. But I want to pause on this slide for quite a while and just walk us through and see how in every facet of this problem orientation, how vital science is. So starting with the goals. We don't even know about greenhouse gases necessarily, let alone able to measure them without science. So on one hand, we live and move around in a world that is intelligible. You know, the wheat grows from the seed and the child turns into the adult and not the other way around. And water flows downhill and it only snows when it's cold. This is a kind of intelligible world with patterns and rhythms that we can understand, and science gives us a precisioning of our understanding of that. That's one way of thinking of science. But also science often has us set aside our common sense understanding of the world because it's not actually giving us an intuitive sense of reality. For example, the table I'm sitting at is 99% empty air, according to the atomic theory of matter, right? That's not intuitive, it doesn't seem that way, but that's a scientific picture of reality. The same here. Science extends our ability to see things that would otherwise be invisible, right? To take account of them. So the climate and greenhouse gas concentrations in the climate, to have goals established around those things really fundamentally requires science. Trends. One of the things science does is just empirically, systematically study what's going on in reality so that we can measure and track changes in the world around us. Okay, that's that graph on the right. There's a trend data. Well, that comes from science. Conditioning factors, another thing that science does, is to help us understand the cause-effect relationships in complex systems. You know, there's solar radiation that affects the climate. There's biosphere changes. There's all of these changes that the humans are inducing. How can we tease those apart and figure out how they relate to each other? Projections. You know, if we're not going to be stuck with reading tea leaves or trying to interpret the cracks in a turtle shell, we can use our understanding of cause-effect relationships and the empirical understanding of reality now to try to build models and different ways to project what's going to happen in the future. And that's also obviously an important part of science. And then alternatives, at least in two senses of that. You need science to develop the technologies that you might use to combat climate change, and you need science to assess the efficacy of whatever alternatives you put into place. So on all levels, science is important, right? Okay, let's talk about science and ethics a little bit. I teach another class on this. I just want to point out, it seems obvious, but let's flag it. The norm of truth-telling in science and honesty. You can't just make up data points. You can't just wishfully think your way into the future or say, I wish it was this way. You know, you're not entitled to your own facts, as they say, right? The other thing, see something, say something, this graphic. Once you have knowledge, you have the moral obligation to act on that knowledge, right? If somebody tells you that the house is on fire and there's a baby in the next room, well, now you know, right? And you've got to do something on that, right? There's this sort of obligation. And then in climate, we often ask, well, why is it that we can know so much but still not do very much about it? Is it weakness of the will? Is it kind of a bystander syndrome where you say, well, I thought somebody else was going to do something about it? You know, that's part of the collective action problem of climate change is we're all sort of maybe standing around saying, I don't know, I think it's somebody else's responsibility. But then again, right? If you got to do something when you know something, how do you really know something? When do you have enough evidence, enough knowledge to really act? And then what action should you take? It's not always as obvious as like saving a baby from a burning building, exactly what you should do. Got a picture of a ship here because this is from a famous 1877 essay, The Ethics of Belief. And the punchline was, it's wrong always, everywhere, and for anyone to believe anything on insufficient evidence. And he uses the example of a ship owner who's going to make a lot of money sending his ship back across the Atlantic loaded with people and cargo. And he knows the ship is getting due for some repairs, but he doesn't inspect the ship and he says, it'll be fine, you know, he's hoping it'll be fine. Well, it's not fine, and it sinks and he loses everybody and everything on board. Well, he didn't do due diligence, which is what Clifford is saying. He should have gathered the evidence, informed his beliefs on actually systematic inquiry. That's another deep relationship between ethics and science. But let me give you another but here. What is sufficient evidence? He talks about don't believe anything on insufficient evidence. Well, there's no magic line for when you've got sufficient evidence. And what if time is a factor and the clock is ticking? You know, I keep thinking about the pandemic, you know, early action to implement stay-at-home measures, for example, even if you don't know quite for sure what the virus is or what it's going to do, you're losing time. So there's this real balance between, should we gather more evidence or should we act now? And that's so true of climate as well. Okay, a few words about why science is important for a democracy. Science legitimizes democratic decision-making. You know, one of the things that makes a democracy is we don't base our decisions on some metaphysical or theological worldviews. You don't vote for, when you vote for somebody new, you're not voting for a whole new metaphysic or theological system. Our leaders are still accountable to reality as it is judged by independent or neutral, maybe, scientific institutions that are not partisan, right? So science is a key source of legitimizing power in a democracy and a source of authority. We have experts, the pandemic again you can think about, or climate change. We need experts to guide public policy. Some theories of democracies would say really democracy is a partnership between experts and non-experts. And the affinity between democracy and science goes really deep. At least ideally, they're both universalist. That is, it doesn't matter your national origin, your race, your religion, your gender, your ethnicity, right? You can be a part of these communities, okay? There's no honorific titles bestowed upon you like kings would give to their sons. It's not a hereditary thing, right? They're both open. That is, they want to be open to new evidence and reform themselves as they learn new things, as they struggle towards truth and justice. The Supreme Court, for example, is always figuring out what it means actually to live up to the ideals of freedom and equality, liberty. The same is true of science. Are we getting a better and better picture of reality, right? And they're both meritocracies in some sense, at least ideally, that you can rise in the ranks, not again on the basis of your gender or your color or your age, but just on your abilities, right? These are important shared ideals. There's also tensions though, and this is important. Equality, everybody has equal rights, everybody has equal dignity. That's key, fundamental to a democracy. Expertise, you're not equal, right? Your Google search does not equal my chemistry PhD. I don't have a chemistry PhD, but that's what somebody would put on a mug, right? And it's true, we're not all equal. And if we're not all equal in terms of our knowledge, then we shouldn't always all have an equal voice when it comes to important democratic decision making. So there's a tension there, and it animates so much of the politics around climate science. Okay, so that's why science is important, but we've sort of been leaning on an intuitive sense of what is science. Well, let's try to cash that out. Akbar did not want me to talk about this. He thinks it's too esoteric. But let me throw you just a few words at it. I won't devote a whole lecture to it. But in a way, modern science is a worldview. And it could be an uplifting worldview. In some ways, I think it is. You think about the 4.5 billion year history of the Earth and our sense of deep time and our sense of deep space that the scientific worldview gives to us. It's really awe-inspiring and mesmerizing. On the other hand, the scientific worldview tells us this is all matter in motion. It's all resources. There's not necessarily a sense of purpose or meaning or good and bad written into the furniture of the universe. And so it can seem cold and alienating. So this is a big picture view of science as a worldview that I'll touch on here and there, but Akbar, again, he doesn't want me to spend too much time on it because he wants to get down to the nitty gritty. So let's do that. So when you see a number after this, it means that's the lecture number. So next lecture, episode 6, we're going to look at science as bodies of knowledge. That is, what do we know? What's in the textbooks and what's in our heads when it comes to climate change? What controversies have been closed and sort of printed down, right? And now there it is. And that's so much of what science in general is. If you think about your understanding of the world, a lot of it is via the testimony of things you picked up in scientific textbooks or other sources of science media, right? So what do we know about the climate? Then there's institutions. Well, who figured that out about the climate? And this one we'll talk a little bit about academic organizations and a lot about the alphabet soup, the IPCC, the UNFCCC, the IEA, the EIA. Right? So who are these organizations that are trustworthy and credible, that are telling us what we know about climate and what we don't know about climate? And then there's science as methods and tools. Science is a form of non-narrative rationality. Halley's Comet is not some omen sent from a demon of bad times to come. It's a ball of rock and ice circling the sun. And when you make that claim, there has to be some standards and tests that you can apply to it to figure out whether that's a valid knowledge claim or not. That's what science is in terms of methods, in terms of tools, and it raises questions about, well, if we're doing the systematic pursuit of knowledge, what is knowledge? Justified true belief. Well, how do we justify it? What is science? What is non-science? What is pseudoscience or junk science? So we'll get into that, episode 8. Then couple of episodes or lectures at the end to say, look, I know you're not going to go spend your life in the primary scientific literature. There are people and institutions that do that for us. They filter it, they explain it, they funnel it down into us. So I want to do a tour of who are those institutions that are trustworthy and doing a good job at this, at least from my vantage point. Then we're going to just say, have a vocabulary list, important concepts or tools. You know, I'm big into tools to give you to make sense of climate change. I just have a bunch of these that I want to put out there in episode 10 once we have a kind of grounding in the science. And then the last lecture or episode in module 2, again, will just be to say, okay, there's the science understood as bodies of knowledge, science understood as institutions, science as the methods and tools like the climate models that we're using. Let's take all of that and try to say, well, what are scientists telling us now about what they think, where we're at, where we need to go, what we should do, or at least what are the important debates around those questions now in the scientific world, because of course it's very diverse and you're going to find lots of disagreement on different levels. Right? So we're going to try to survey that, make some sense of it. That will take us into module 3, which will be about climate science in context. We'll just call it climate politics, where we look at how all this plays out in the problems that we're debating in the public sphere. So that's that. Akbar reminds us that cool humanoids cruise in carbon neutral spaceships. And until next time, may the force be with you.